Hello everyone, welcome back to our lectures. Today we're going to start talking about two variation of Adams algorithm. First, let's review what we have for Adams algorithm before. Previous lectures video, we talk about Adams algorithm, and the algorithm itself has two different momentum. The first is the first order momentum V, and the second is the second order momentum S, noted here. And each one of the momentum are updated with using a beta 1 and beta 2. These are the so-called exponential smoothing parameters. And the beta 1 represents how much I will trust the past momentum, Vt minus 1, and also represent what kind of confidence I have on the current gradient itself. Similar situation apply for the second order momentum. And the second order momentum S represents how much trust I have on the previous second order momentum, plus the rest of the confidence I have on the momentum squared. And typically we choose beta 1 equals to 0.9 and beta 2 equals to 0.999. So actually we have a pretty good confidence on the previous momentums instead of a current gradient. So we give the current gradient's information, or gradient's square of a gradient information, less of the concern. With that, I'm going to also divide both sides by 1 minus beta 1 or 1 minus beta 2. We call it calibrated or unbiased first and second order momentum. With that, we can calculate this so-called G-prom, which is calibrated or corrected gradient, and use that to update my new solution. Okay, so the concept is including the first and second order momentum information into a so-called corrected gradient. This type of concept using a so-called exponentially smooth or exponential moving average type of a concept is not new, but it also is created quite a bit good convergence of behavior. So last time we had a full-blown of exploration on this Adam algorithm, and we showed that it is fairly stable in a sense. Today I want to introduce two variations of this Adam algorithm. The first variation is called Yogi. Yogi is an algorithm trying to modify the update for the second order momentum, get an enhancement of the. So here you can see that from the second order momentum, since ST initially is 0 and GT square is always positive, and so this ST itself is continuously increasing. Okay, and so the second momentum is always increasing. So this could have some issue with it if the algorithm prolong for a long time, this second order momentum becomes bigger and bigger. Okay, even though it's smoothed out by this exponential weighted factor, beta 2. So here is trying to see if we can improve this type of situation. The other is the The other method is called Adam algorithm with Nestrov momentum. So we're going to replace this part, the GT part, with the Nestrov momentum instead of using directly the GT. So one of the algorithm variation is trying to change the first order momentum, and the other one is trying to change the second order momentum. Let's start with the first one called Yogi. Yogi is proposed by four Google analysts and programming analysts and trying to improve the current Adams algorithm in 2018, I believe, and 2004, I think 2019 and 2018. I think the 2018 is the main references here. The idea of the Yogi algorithm is the Yogi's name coming from ancient, talking about this first enhancement called Yogi. Yogi is an enhanced algorithm talking about trying to modify or improve the second order momentum using the second order momentum with a sign. And Yogi's name is coming from ancient Indian dialect called Sanskrit. Is the yogi means it's add, because I think one of the author, several of author in the original articles are from that region, so they're using the ancient Indian languages called Yoi. Yoi means add. So here what we have is, instead of using the traditional exponential smoothing method to update the second order momentum as Adam does, it's still using the original 1 minus beta 2 times the g squared as update the second order momentum. And however, it multiplied by a sign, the difference between the current gradient square minus the st. So st is st minus 1 basically, and it tells you what is the changes in magnitude of the gradient, and basically so therefore this portion has a sign. I can either plus or minus within that at different direction. The parameter tuning is about the same, and beta 1 usually equals to 0.9, beta 2 equals to 0.999, still giving the the current past momentum or past first and second order momentum more of the confidence in that sense. V hat and S hat are the calibrated first order and second order momentum. The calculation of the so-called corrected gradient is almost exactly the same, and the update is exactly the same. So here, what we have for this Yogi algorithm, the only changes in the equation 1 will change the way we update our second order momentum S. The implementation is very simple as well. It's very similar to our previous lectures on atoms, so I'm not going to go too much detail. First, we plot the surface, define the functions, see if everything okay. And also we can plot the so-called contour chart, contour graph for the function. And we give you the first order and second order, the objective function, what it looks like, and the first derivative and what it looks like. The subroutine I just cut and paste from the Adams algorithm, and we call it Yogi subroutine function. Only thing difference is this line, this line of how we update the second order momentum. Okay, and V hat and S hat update are exactly the same. How we update the new solution X is exactly the same. And convergence criteria, I still set it to 10 to minus 5 here. And if they satisfy the criteria, we terminate the algorithm early. Otherwise, we let it run whatever maximum number of iteration prescribed. The main program we have is the same thing, and using the same C101 and trying to using maximum iteration is 1000 and step size is 0.02. Okay, this is also suggested by the literature for a nice function like this. The same thing we trying to using the called the Yogi algorithm, and we define the objective and derivative. Also, the bound from the variables, I set it to -1 to 3 for x, -1 to 2.5 for y, and alpha, beta, and beta 2. Alpha is the step size alpha, and beta 1 is the exponential smoothing factor for the first order momentum. Beta is the smoothing factor, exponential smoothing factor for second order momentum. After we set it up, we're running, trying to solve this Rosenbrock function again. This time is fairly lucky. We take only 47 iteration to converge. And the solution quality looks pretty nice, all close to 1. We know the true optimal is 1 and 1. And the optimal objective function should be 0. So the solution quality is okay, and it only takes 47 iteration. It takes almost 6,000ths of a second, and so it's very insignificant. The next things I want to show today with this particular lecture is trying to show you the trajectory or the step of the solving. I'm using a various of step size to demonstrate. What I have is almost the same thing with we have before defined the objective function and derivative. I call it objective function 2 and 2 over here. The Rosenbrock function and the derivative of Rosenbrock function. And just cut and paste the Yogi subroutine over here. Okay, you can see that I just cut off the convergence criteria check. Okay, I just print out each iteration. Finally, we show you the final. The purpose of this algorithm, this subroutine right here, Yogi, is demonstrate the trajectory of a solution point. The main program is almost the same, cut and paste. However, I start trying the different step size. Beta 1, beta 2 stay for the suggested value, so I didn't change that at all. Slightly shrink the negative part of a variable bound because we know the solution is 1 and 1, so we can see that trajectory better. It's just for the cosmetic purposes. I'm trying to do is and for xy, all the xy, so each solution, each time I solve the problem, I append the current solution into a list called solutions. The solutions is all iteration t, range of a number of iteration. Each iteration, I save that current solution into a list. And then we're going to plot that list. Okay? So first we create a mesh grid for X and Y and calculating the Z value, which is objective value for each one of the X and Y. We plot the contour chart for contour plot for X and Y, and Z. Z is the result, which is this objective function value. Next things we do is we using the solution list and convert it into NumPy array as array. We plot each one of the data points on this contour chart using the white color. Plot the last point, okay, on the solution using a red dot. So here is, I run it for 400 replication and see what happened. Notice here I'm using a fairly large alpha equals to 1.0, and it also converge pretty nicely. If you can look at this, it's not converging too quick, but still uniform converges pretty well. I just let it run for 400 iteration, and now you can see the trajectory. And the point is started with here, okay, over here, and zigzag in the beginning, and even out of the boundary we can plot, and it come back, and later part of the, once it getting closer to optimal solution, and a zigzag becomes smaller and smaller. Since the step size is still pretty big, so you see that in the zigzagging still going on in that sense. We give 90% or 99% of the confidence on the previous momentum, so the momentum eventually dominates the current gradient information. So this will converge nicely, and you are welcome to try with a different. Let's see if I can try a different lambda. So for example, I shrink the step size for 10 times, so 0.1 instead of 1, and running for 400 iteration. And you can see that it started from the different location, but however it comes in and converge to the optimal solution is not as close. So we can do a try and error on the how sensitive this algorithm is to the step size we predefine. Okay, and this is another trial. You can see then in this algorithm converge to a fairly close to optimal within 400 iteration. So this is give you idea how different size of alpha, you can see the trajectory, how the solution path going. And okay, this is what we have for this lecture, and then we're going to talk about the so-called Adam algorithm with Nestrov momentum in the next lecture video. Bye-bye.